Yeah. Good afternoon, dear students. Today we will discuss AVL trees. So, as we have discussed in the last class, binary search trees, right? So, we have discussed the properties of binary search tree. You know, and the objective behind binary search tree as well we have discussed, right? In order to make the time complexity on linked list searching to be logarithmic, as how we could able to achieve with the help of binary search when we are applying on arrays. We wanted to organize this list in the tree order. So that's how exactly binary search tree invention could have taken place. And as per our expectation, the time complexity of binary search tree we said should be logarithmic. That's well and good. And as per the properties of binary search tree is there is a special node called root, and left subtree of which are lesser than root, and right subtree of which are greater than root. This is the property, and which help us in rescuing certain part of mm, nodes from being compared, like how binary search allows us. That way it could able to achieve us the logarithmic time complexity. Like that's fine, but then when you're trying to insert these kind of elements, we have said, the sequence, the order in which the elements are given, the first element will be considered as the root, and the subsequent element will be added either to the left or right based on the value when being compared with the root. If it is less, it goes to the left, or if it is greater, it goes to the right. That way, when we have given a sequence of elements of this kind, where we can see the tree could have been formed of this kind, right? That's fine. But then what happens when I give the elements with the help of which a skew tree is formed? Like, for example, the sequence of element with which I have to now, let us say, construct the binary search tree is, let us say, 10, 15, 20, 25, and 30. You start the first element with the root, then subsequent element will be just added to that existing tree by being compared with that root, if it is greater to the right, right? And that way, when you add 20 by where it goes, it goes to right of 15. And then when you add 25, that goes to the right of 20. And when you add 30, it goes to the right of 30. So in this case, now the tree is formed. This is called right skewed tree, right? This is called skewed tree. So there is a possibility of skewed trees could have been formed, rather, right? Based on the sequence of values that you rather give. This is anyway right skewed. Similarly, a mirror image of that is of this is said to be the left skewed tree, right? It can be like this. Okay, if you have a tree formed like this is said to be a left skewed tree, right? So whether it is a left skewed or right skewed tree, if you take an element to be rather set, for example, in this right skewed, if I am trying to search at, let us say, delete 30, what I have to do, I have to perform how many comparisons right from root. I start scan forward until I get that particular element. So let us have an example here in this case about 5 elements. So until I get my node on which I rather have to kind of operation to be performed will take around equivalent to the number of nodes. So the time complexity, it becomes here big of n. It's not logarithmic, rather, right? My main objective behind coming to binary search tree is to achieve the time complexity while performing the operations like insert, delete, or search with basically logarithmic, right? So, but then search operation, if you see in a kind of this right skewed or left skewed tree, is polynomial, not logarithmic, right? Now, what should we do? What kind of solution we can rather apply? So we need to balance this binary search tree. If we can balance the binary search tree, right, then again we can probably rather achieve the same kind of time complexity as logarithmic, right? Logarithmic time complexity can be achieved only when we have the balanced binary search tree. Yes or no? So on this is said to be what? This is said to be the full binary tree, right? So in full binary tree, you can find the height of both left and right is always equal on every node, rather, right? Uh, when you find the height of both left and right of every node is equal on binary tree, then it is said to be full binary tree. And what is complete binary tree? In complete binary tree, even in complete binary tree as well, you can able to achieve the time complexity in logarithm when you are searching an element rather, right? So when you are saying it is a complete binary tree, when you find the leaf nodes available on the, this is said to be if I am saying, let's say this is h level, this is h minus 1 level, and like that, and this is the 0th level, right? So at h level anyway you will find, that is the last level rather, right? At h level anyway you will have the leaf nodes on any tree rather, right? But in addition to H level, at H minus 1 level as well, leaf nodes can be possible rather, right? And at H minus 1 level, you can rather have a single subtree, that is left subtree or right subtree, okay? This is also a complete binary tree, right? This is also a complete binary tree. So a complete binary tree will have the elements equivalent to, if the height is, let us say, h, then in what it could be, 0, 1, this is level 2, right? So number of nodes with height h in complete binary tree of minimum could be around how much? 2 power h, right? 2 power h is the minimum number of nodes, right? In a complete binary tree you can have with height h. And what could be the maximum number of nodes that you can have? These are the maximum number of nodes rather, right? So 2 power h plus 1 minus 1, right? You can see how many nodes you have. So 7 nodes, right? This is maximum, right? This is maximum. So in complete binary tree, the maximum number of nodes that you can have is 2 power. This is a complete binary tree and as well a final binary tree. But this is only a complete binary. This is not a final. It means that all full binary trees are complete binary trees. Yes or no? All full binary trees are complete binary trees. Whereas all complete binary trees may not be full binary trees. Yes or no? May not be full binary trees. All complete binary trees may not be, because this complete binary tree is not a full binary tree. But if I add another node, this is still a complete binary tree, right? If I add another node, this is still a complete binary tree. If I add another node, this is still a complete binary tree. This complete binary tree is having with maximum number of nodes with height h. But if I remove these, right? If I remove this, the minimum number of nodes it forms with rather. But it's even said to be the complete. So here, our idea behind, to bring the time complexity into logarithmic, if the tree is in the form of either full binary tree or complete binary tree, then again you are able to achieve the time complexity in logarithmic, right? So now, in pipeline to the same, balanced binary search trees have been evolved, right? Balanced binary search tree. So we have, AVL is one of such kind. Okay, red black tree is another kind of balanced binary search tree, rather, right? Red black tree or split trees. These are all the balanced binary search tree, I can say, right? So if you see Anderson, Belsky, Landis, who have invented this in 1962, they are the mathematicians rather, right? So AVL tree is not any separate tree, rather it is a binary search tree only, but it is a balanced binary search tree. Understand? So so what the aim behind in constructing this AVL tree is to ensure that the time complexity to perform any searching operation on the particular tree should be logarithmic, right? This is our objective behind going for this AVL tree. AVL tree is not a separate tree, rather it is a binary search tree itself, but it is a balanced binary search tree. So the properties of an AVL tree, if you probably look at the properties, height difference, height difference of left and right should not exceed mod 1. What do you mean by it? That is the height of the left subtree minus height of the right subtree should always be less than are equal to 1. What do you mean by it? When you take the difference of it, it could be either plus or minus, right? But when I'm taking mod, in the sense I'm taking the positive value out of it, so it should be not less than or equal to 1. So till 1 it is permitted, right? The height difference should not be more than 1. It means it should be 0 or 1. See, in this case, what is the height difference of all the nodes in full binary? It is 0. See, left subtree you don't have, right subtree you don't have. So what is the height difference that we are calling it as a balance factor, right? The balance factor is nothing but the height difference, right, of left and right side. So balance factor of this particular node is 0. This is 0. This is 0, because here you have left is 1, right is 1, 1 minus 1, 0. This is no 0, 0, 0 minus 0, 0, 0, 1 minus 1, 0. And if you go here 2, right, this is 1 level, this is 2 level. So height is 2, here is 2. 2 minus 2 is going to be 0. In full binary you can find the balance factor is 0. So it is perfectly AVL tree, right? This is perfectly AVL tree. Now coming to complete binary tree, if I remove all this, if I remove this, right, what is the balance factor of this? This is 0, but this is going to be 1 minus 0 is going to be 1, right? And this one is 0, but this is going to be what? 1 minus 2, 2 minus 1 is going to be 1. It is still an AVL tree, because you can see the balance factor is not more than 1. It is 0 or 1. So it means all complete or full binary trees will satisfy the AVL property, rather, right? Concept. Fine. So taking this concept into consideration, we are trying to construct the balanced binary search tree with the help of the AVL tree. So when you're performing insert operation or delete operation, it is very similar to that how we have performed on binary search tree. Okay. So after you perform the insertion, then you need to ensure the balance factors. Ensure the balance factors of all the nodes due to the new node insertion should not exceed more than 1. So generally what happens when you are trying to insert a node, it could be either left subtree or it could be inserted into the right subtree. So the part of the tree in which the path otherwise around, the path across which that node is newly inserted, across that path you need to ensure the balance factor is not exceeding 1. If you find any of the node across this path, right from the node where you have inserted until you reach the root exceeding 1, then you will have to balance it. Okay, so that balancing generally is required in 4 of the situations. There are 4 different cases you probably encounter with, rather, right? When you're trying to insert a node into the left of left subtree, where already left subtree is having height 1 more than its right subtree. Got it? For example, you have a node, let us say this is 50, this is 40, and here you have, let us say, 30, and here you have, let us say, 60. This is a tree you have, right? So now, is it an AVL tree? Yes, it is an AVL tree, because it's a complete binary, right? You have the balance factor is 0 here, and this is 1 here, this is 0 here, this is 1 to 2 minus 1 is going to be 1 here, right? So this is a AVL tree. But then let us say you are trying to insert what? 25. Okay. Now you are trying to insert 25. What happens when you are inserting 25? Where it goes? It goes to the left of 30. Yes or no? But if you look at here, the 40, this is the node which is available to the left of 50. Basically, when you insert this 25 and you update the balance factor, what happens? The root is going to be get imbalanced, right? And here even this node is going to be get imbalanced, right? So across the path in which the node being inserted, you will have to start updating the balance factor until you reach the root. So wherever you find the node is having more than 1 its balance factor, then it is imbalanced. So in that case you will have to apply the rotations and then bring back into the balance tree, balance option, right? So here what happens is, you can see before insertion of 25, you can see the left subtree of 50 was already having the left, its left subtree height more than its right subtree, because you don't have, it doesn't have right subtree, and its left subtree is 1, right? So the left subtree of 50 was already having left high. When it is 1, I say it is left high. When I am using some notations here, 1 for left high, -1 for right high, and 0 for equal high. Okay, so you can see here the 40 which is left to 50 was already left high, because it doesn't have right subtree, and it was having left subtree, right? So the node which is already left high, into which again you have inserted of its left rather, right? Then with that, what happens, its left subtree height will become further increased rather, right? So it means this balance factor is going to be now 2. Yes or no? This is going to be 1 2, this is 0, and this is going to be 1 rather, right? And this becomes what? 2. Yes or no? Right? It doesn't have, right? That is 0 here. So here you can find 0, this is 1, this is 2. Now obviously this is going to be 1 2 3, 3 minus 1 is going to be 2. But then right from the node, you have to reach until the root across the path, and wherever you find a node is imbalanced, you'll have to first balance it. From there on until you reach the root, you have to do this kind of adjustments rather, right? So now when you see here at 40, what happens is this is imbalance. So this particular situation is said to be left rotation, right? LL rotation we call it as, right? LL. So LL in the sense, see, the left subtree height was already left high, and you have inserted the node into its left of the same. That is, when it was already left high, you have inserted into its left. So that is said to be left rotation. What is the solution for left rotation? Right? Apply right rotation on this node, right? You have to apply right rotation on the imbalanced node rather, right? When do you say left rotation? Basically, the node, when your node inserted into left of left subtree, yes or no? This is the left subtree of 50, into its left only you have inserted, right? That is said to be left rotation. So in a left rotation, what is the solution? Apply right rotation. Apply right rotation on the node which is imbalanced. So here 40 is imbalanced, so you are applying the right rotation. So when you are applying right rotation, how do you apply the right rotation? Basically, see, to the right of this left, it is null, right? This is null, yes or no? So you will attach the right of left to the left of 40, and then 40 will go to the right of 30, and 30 will occupy this position. Understand? These are the 3 steps that you are going to do it, right? If I say this is the node to be rotated to the right, so let us say this is temp, okay, and let us say this is your right of temp, right? Sorry, left of temp. So let us say this is L. So L equal to temp left, right? So what is that you do? The right of left is here null anyway, right? If you have some node, then probably you have. So right of L right of L has to be attached to the left of this temp, right? Or you say temp right, okay. This is the first step that you do. Next is you will take this L and attach to the replace it with the temp. Got it? So it means now what happens? This temp is actually, this is your root here. So temp is nothing but what? Root left, right? temp is root left. Yes or no? How? Temp is root left. This is your root. Now when you are applying right rotation here, what happens? You have taken temp left in L. Okay, temp left in L, and then the right of L is going to be get attached to the temp right. In temp right you will be attaching, it is null anyway, so null. Then you will take this L and then attach it to the root left, right? So this L will be attached to the root left. In root left earlier temp right, now L is going to be get attached. This is the algorithm. Fine. So then what happens when you apply this rotation? Now with these changes, what happens is you will get 50 of course intact, but then to the left you get here 30. Yes or no? See, what is that you are attaching to the root left L? L is nothing but 30. So in place of 40 you get 30. And to the right of 30, that is to the right of L, you can see you are attaching what? The temp left. This has to be attached to the right of L. Okay, so L right equal to what? Temp. L right. So in right of 30 you get what? 40 here, and this is unchanged 25. Then this is unchanged, right? So these are the steps. This is your root. What we have done is, in case 1 with left rotation, okay, we have taken temp pointer and we are holding the root left. This is root left, so temp is here. Now L is here. L actually want to point to the left of the temp you want to hold. So L equal to temp left we said. So L is here. Now L right. This is L right. L right is null anyway. That we are placing in the left of because left of temp is holding this one, right? Should be left here. Sorry. Fine. So temp left equal to L right. L right is null anyway, that you are placing in the left of temp. So earlier temp left was holding this. Now it holds nothing because this right will be taken there. So that is null. So that it becomes null then. Then next thing is L is going to get attached to the left of root. You can see, right? And then this temp is going to be attached to the L right. So in L right you will get 40, L right you will get 40, and 30 will go to the left of 50. Now you can see after you apply the right rotation on this particular tree, due to the insertion of 25, your tree becomes like this. Is it now AVL? Yes, it's AVL, because when you check the balance factors, it is 0, 0, 0, 0, and this is going to be 1, 2, 2 minus 1 is going to be 1, right? So now it is fine. So due to every insertion, if balance factors get changed and if it is violating the AVL property, then you have to ensure that it is brought back into the balanced one, right? So what are the extreme cases that you may found as nothing but this is one case, this is case 1, okay? And similarly you may encounter with another case that is said to be case 2. Case 1 is what I said is the left rotation, right? And the mirror image of the same is nothing but right rotation, mirror image of the same, right? These rotations are said to be the single rotations as well, right? So this generally happens. For example, if I have a tree like this, you have a tree like this, okay? Now when your tree is like this, you can see here tree is AVL, yes, because the balance factors is 0 here, this is -1, This is 0, this is minus 1. Good. Fine. Now I wanted to insert, let us say 75. Okay. Insert 75. What happens? Where it goes? It goes to the right of 70. Now what happens if you look at the balance factors? This is 0, this is minus 1, this is minus 2. It means this is exceeding the balance factor value more than 1 rather, right? So this is imbalance. So the node due to which the balance factor across that path is being, you know, deferred from more than 1, then all such nodes you have to bring back into the not more than 1. So that's how you can again restore the property of AVL, and this process has to be repeated until you reach the root node rather, right? So this is what exactly you're trying to do in the AVL tree. Now when you're inserting 75, what is happening, you can see here. Yeah, this particular scenario I'm calling it as right rotation because see this node which is right to 50, which is already right high. Minus 1 means right high. Okay, the node which is already right high, into its right you have inserted, not in the left. If you would have right inserted into the left, there is no issue, you would have got right. It was still in AVL. But then when a node is already right high and you are trying to insert a node into the right of it, it means either to the right of 70 or left of 70. In both the cases you get that rather, right? I wanted to first go with right rotation. So in that case, what happens when you're trying to insert a node into the right of right subtree, because of which it get violated from AVL property? Fine. Then what is the solution, right? How could you encounter this particular problem is node inserted. Node is inserted into right of right subtree. When right was already right high. Got it? So what is the solution for this? Solution is apply left rotation. Apply left rotation. Now look at the algorithm, right? Left rotation algorithm. It is mirror image of the right rotation. Exactly mirror image of this, right? What you do is this is your root, right? And take this in temp. Okay, that is a root right. You're taking in temp. Okay, then take this in R. Another pointer R I have taken. R equal to, I'm saying temp right, temp right. Okay, now here it is null, right? The left of right R. So left of R you will be assigning to the right of temp. In temp right, you will place what? R's left. Exactly. Just replace left with right, right with left in this algorithm. It becomes a right rotation because left rotation and right rotation are mirror images, right? They are symmetric in nature, right? So I'm just replacing left with right, right with left. Also, I'll get this algorithm, right? So attaching the left of R to the right of temp, that is what you have done, and then this has to be replaced with this, right? It means R will go and get attached to the right of root. Okay, so root right, root right get what? R. Okay, So R will come here. Then this will go, temp will go to the left of R. Okay. So left of R left I'm saying, right? R left equal to temp. That's it, right? You apply this, and then what happens you can see here. When you apply this, see the right of 70 goes to the, sorry, left of 70 goes to the right of 60, means 60 right will be null, left was already null. Okay, then 60 will go and get attached to the left of 70. It means 70 left you will get 60, and to the right it was already 75, it is intact. Then this 70, that is R, will go and get attached to the right of root. Okay, so you can say root right equal to R, you are saying, right? So here that 50 will go and get attached, and then 40 will be unchanged. So this is your tree after you apply this rotation. So now when you look at the balance factor, this is 0, this is 0, this is 0, this is 0, this is -1. It is in AVL, right? Yes or no? It's in AVL. So it means here these are the two cases, and there are two more cases that you may encounter with when you are trying to insert a node, because of which AVL tree property can be violated across that particular path in which that particular node was inserted from the root. Okay, so these two rotations are said to be single rotations, right? Left, left, or you can say LL rotation, or you can call it as this one, you can call it as RR rotation. Another two cases are said to be the double rotations as well. So case 3, that is left right rotation, LR, left right rotation. Okay, let us say for example you have the nodes to the left, you have inserted into the right of it. You have a tree like this, till here there is no issue, but then if you have inserted to the right of this, what happens? Let us say I'm inserting 35. Okay, where does 35 goes? It goes here, right, to the right of 30. Yes or no? See, my tree before 35 is inserted was in AVL, but then when you insert 35 here, this is 0, this is -1, this is 2 minus 0 is going to be 2, and this is 0, this is also 2 rather, right? So now across the path, if you see here, you got imbalance. So now this particular node has to be balanced. Now for this particular node to be balanced, you have to apply two rotations rather, right? You have to apply two rotations. So 40, 30, 35, right? One rotation that you have to apply on 30, that is left rotation. Left rotation on this node, and then you have to apply another rotation, that is right rotation on the root. Fine. Since you are applying two rotations, I say it is a double rotation, right? So if this is the scenario, what happens? First, when you apply the left rotation on 30, apply the algorithm which I have discussed before rather, right? So here anyway, you must be having, here it is null anyway, in this case. Yes or no? This is null anyway. So when you apply a rotation, left rotation on 30, 35, what happens? How does it becomes? It becomes like this, right? 35, 30 when you apply, right? And you have 40 before. Now when you apply right rotation on the same, what happens now? You get 35, 40 and 30, right? And this will be replaced in place of this. Okay, then your tree becomes 50. To the left you get this tree, right? That is 35, 30, and then 40, and to the right this is 60. See why these rotations are applied, and the rotation mechanism algorithm is written in such a way that it should not violate again BST. The basic property of AVL tree is a binary search tree, right? So first it is binary search tree. Got it? In binary search tree, the root value must be greater than its left subtree and lesser than its right subtree. That has to be intact, rather, right? Now your tree, this tree will become like this. Okay, when you apply the two rotations. See, this is the problem. The node 40 got its balance factor 2, and why it is 2? Because it's into its left. The balance factor, if you locate, it is right high. When the balance factor of the left subtree is right high, then you will have to apply two rotation. One is you apply the left rotation on the left subtree and apply the right rotation on the root. Okay, so this is the tree I am taking to apply the rotations, right? Then this becomes the root for me, right? And this becomes the left of the same. So what is that you are doing? Applying the left rotation on the left subtree and applying the right rotation on the root, then your tree becomes this. So in place of this, what do you get? You will get this at the end. So you will now, when you get the this part of the particular tree will be replaced with this after the rotation, and update the balance factor. The balance factors are now what? They are within the range. They are satisfying the AVL property, right? This is said to be left right rotation. And another case that you may encounter is with case 4, right? So after you insert the node, when you update the balance factors, you will have to see under which particular case you are falling. Based on that, the mechanism you're going to apply, right? Then another case is a right left rotation. Okay, right left rotation. So in this right left rotation, for example, you have a tree like this. Now if you can see, the balance factors are good, right? This is 0, this is -1, this is 0, and this is -1. But if I have inserted, let us say 65, where does it go? You start right from root, right, to insert any node. Compare with the root. If it is greater, move into its right. Then it is greater, so you move into its right, but it is lesser, so you move into its left. So 65 will be inserted somewhere here. Now when you have inserted 65, what happens? The balance factors, when you update, this is 0, and this is going to be what? This is going to be 1, right? And this is going to be what? -2. This is imbalance. Then you have to first bring this particular node into balance, right? You have to make it AVL. So this particular case is said to be right left. When your right subtree into its right subtree, if you have inserted the left subtree, because of which that particular node is violated, then it is said to be what? Right left rotation, right? RL. See, the left is inserted to the right of this particular root, because of which this particular node is being deviated from the AVL property, rather, right? So in this particular scenario, right, this is your tree which is imbalanced, right? So now what is that you're going to do? You're going to apply two rotations again, right? You first apply right rotation and right subtree. See, if I take this particular tree, this is my root now, and this is my right subtree, right? So apply the right rotation on the right subtree, then apply the left rotation on the root, right? So when I apply the right rotation on the right subtree, what do I get? I'll get 65, 70, and then above it will be 60. Now I have to apply left rotation of the root. When I apply left rotation of the root, what do I get? I'll get 65, then 60 here, then to the right I'll get 70. Now I have to replace this with this particular node. So then my tree becomes this tree, right? This tree becomes now 50, To the left it is 40. Now to the right you will get this particular tree, that is 65. Yes or no? To the left it is 60, to the right it is 70. Now update the balance factor. 0, 0, this is 0, this is 0, this is 1, 2. 1 minus 2 is going to be minus 1. It is AVL, right? So no issue. So these are the four cases that you may encounter with when you are basically inserting or deleting any node from the AVL tree. So what you have to do, you have to ensure after you either insert or delete into in AVL3, right from the position across which you perform this operation, until you reach root across that path. If any node is deviated from the AVL property, that is its balance factor when updated is having more than 1, then you have to ensure that it is coming under which particular case, whether it is LL rotation, LR rotation, RR rotation, or RL rotation, right? LL, RR are said to be single rotations. They are symmetric in nature, and LR and RL are double rotation. They are symmetric in nature, right? So applying these rotations again, you will bring back that particular node into AVL, and then again update the balance factor, and then you reach until the root to ensure that all the nodes are satisfying the AVL property. Right. This is what exactly you have to do while you are, performing the AVL. Let us look at the small PPT. I have a presentation. I hope this is clear to all of you. The concept is clear to all of you. Yes.
Yes, sir.
Yeah, now let us look at this PPT. As we know, data structure is a structured set of elements. Consists of when you classify, they are about linear and non-linear. Under linear, we have seen arrays, linked lists, and all. For which stacks and queues we have implemented using both arrays and linked lists. And under non-linear, you find trees and graphs, right? So coming to binary search tree, as we have seen, binary search tree property. The basic property of binary search tree is there is a special node called root, and the left subtree of which will have lesser than its root, and the right subtree will have values greater than its root, right? Now the problem is actually as long as binary search tree is a full binary search tree or a complete binary search tree, then you will be able to achieve the time complexity in logarithmic. But in a very worst case scenario, when the height of the binary search tree is n minus 1, you will be resulting with a polynomial, that is big O of n, right? So then in that case, what do you have to do? In order to reduce the time complexity to logarithm, you have to reduce the height. Find how you are going to reduce the height is what exactly, where these balanced binary search tree are going to help you out. There are certain balanced binary search tree which are available, like AVL and red black trees that are as part of a syllabus we're going to study, right? So the left and right subtree of root have the same height, then it's very good. Every node must have left and right subtree of the same height. That's very good, right? Our choice for each node, the height of the left and right subtrees can differ at the most one. This is what exactly some of the suggestions that were made before the balanced binary trees came in existence. So, taking these suggestions, AVL tree, Anderson, Belsky, and Landis, two Russian mathematicians in 1962 have proposed one solutions for balanced binary search tree, rather, right? So you can see the first one satisfying the AVL property, but the second one is not satisfying. Why? Because the balance factors at 7 is not 1. At most, we said 1, but then it will have 2. 1, 2, 3. 3 minus 1 is going to be at 7, you're going to get 2, right? So, which is not balanced, rather, right? So, some of the AVL trees with the balance, 1, where the balance factor is not more than 1 is, some of them are listed out here. With height n, you can have AVL tree of this kind, where the balance factor of all the nodes not exceeding 1. Okay. Now our issue majorly is to ensure that our height should not get increased, right? So so after all this observations, what we have could come across with a solution that we have to rebalance, right? It is better if we probably do the balance check in the path where exactly that particular node is inserted, rather, right? So the rest is anyway is in balance, rather, right? When you are basically deleting the node also must be rebalanced. Basically what happens, there are four cases that I have basically discussed with you, have been here listed out again. An insertion into the left subtree of the left child of A, that is left left rotation. An insertion into the right subtree of left subtree, this is LR rotation. An insertion into the left subtree of the right child of A, okay, RL. And insertion into the right subtree. So these are these four cases that you may probably encounter with when you probably observe 1 and 4 are symmetric in nature, that is LL rotation and RR rotation, and 2 and 4 are nothing but what, RL and LR, they are also symmetric in nature, right? So we have to rebalance the AVL tree, with these kind of notations, with this kind of rotations, rather, right? So this left left or right right, where only single rotation is applied. In left left, you are applying the right rotation on the node which is deviated from the AVL property, rather, right? In right right, you will be applying the left rotation. In left right, you will be applying the right on the right and then left on the root. And right left, you will be applying left on the left and then right on the root. Okay, so this is how you perform when you apply the rotation. You can see the rotations are symmetric in nature. I said left rotation and right rotation. If you apply the right rotation on the first tree, you will get the second tree, the tree which is available on the right side. Fine. If you apply the left rotation on the same which is available on the right side, you can be able to extract the left. It means they are symmetric in nature. They are mirror images, rather, right? So these are the four cases that I have already discussed, right? Left left case, right right case, left right case, and right left case. In left left, what is that going to do? You are just applying the right rotation on root. So when you have a tree like this, 5 3 2, apply the rotation, 3 will be the root and 5 will go to the right of it, right? In right right, that is when you are trying to insert a node into the right of right subtree when right is already right high. Okay, in that case, you will be applying the left rotation on the root. So then what happens? 5 will occupy the right will occupy the root position, rather, right root will go to the left of the root, left of the right. Okay, so 5 3 4 7 you get, rather. Left right case, that is LR case, when you have already the left subtree height is right high, you are trying to insert into the right itself, then it is said to be left right case, right, wherein you are applying two rotation. One is on the right rotation on the left rotation on the left subtree, and then right rotation on the root. And in right left case, what will you do? You will apply the right rotation on the right subtree and left rotation on the root. Okay, so these are the solutions that we have suggested and adopted in order to make the tree bring back into the AVL kind, rather, right? So taking these all into consideration, one sample example here been mentioned. When you are trying to insert, let us say 3 2 1 4 5 6 in the sequence, 3 initially, I mean whatever the first node, that becomes the root, rather, right? So 3 is root, 2 will go to the left of 3. Then when you are inserting 1, what happens? Until 3 2 it was in AVL, because 2 balance factor is 0 and 3 is 1, so 0 1 is in AVL. Only when the balance factor is exceeding 1, you say it is violating AVL, and you have to apply the required rotations, inspecting which particular case it is falling under, rather, right? So when you are trying to insert 1 over here, it goes to left of 2, but then because of which 3 get its balance factor 2, which is violating the AVL property, then you have to apply rotations, which particular case it does come under, that is left left LL rotation, where you have to apply the right rotation on the root. So when you apply the right rotation on the root, 3 will go to the right of 2, and 2 will occupy the root, like that. You can see similarly, when you are trying to insert 4, no issue. When you are trying to insert again 5, you got an issue at 3. So this is said to be again RR rotation, right? When the right was already right, when the right was already right high, you are trying to insert into the right. So in that case, what happens? You will be applying the left rotation on this particular 3, rather, right? So when you apply left rotation, what do you get? you'll get 4 will occupy 3 position, 3 will go to the left of 4, like that you can see here. Apply a single rotation. Similarly, when you're trying to insert 6, 6, because of 6 what happens, 2 will get in a problem. So here again, what kind of rotation is required? Single rotation, that is left rotation on 2, because you can see the balance factor of 2 gets changed to -2. This is what is the height of right subtree of 2? 1, 2, 3. In the left it is 1. 1 minus 3 is going to -2. So 2 is having -2. And this comes under right rotation. When its right subtree was already right here, you have inserted into it, right? So you'll be applying the left rotation in RR. Fine. So of the root. Then what happens? 4 will occupy the root position. 2 will go to the left of 4. But before that, left of 4 will be attached to the right of 2. You can see left of 4 is what? 3. So that will go to the right of 2, and 2 will come to the left of 4, and 4 will occupy the root position. This is what exactly the algorithm we have mentioned, rather, right? You can just go through. Applying those algorithms here, the continuation of insertion of all these nodes is done, and as and when the rotations are required, whenever you find a particular node is being violated from its AVL property, the appropriate rotations are applied and ensure that it is brought back into the AVL kind. Okay. So here in this case, you can say double rotation, right? When you're trying to, before 15 inserted, the tree was in AVL, but when you insert 15, what happens? It is not in AVL. So you have to apply a right rotation on 16 and left rotation on 7, right? So then it becomes like this. Okay. So you can see here those examples, double rotation examples are also mentioned here. So here again, this is again a double rotation. You can see when 15 was already right into the right of 4, actually you have inserted, but into the left of its right. So then what happens? It has to be a double rotation again. You have to apply a left rotation on 15, and then a right rotation on 6. So what do you get now? Here you can see when you apply double rotations here, you'll get the tree brought into this particular nature, rather, right? 7 will occupy 15 position, right? And 14 goes to the left of 15, 15 comes to the right of 7. So you will get 7 here somewhere, right? If you can probably see, I just wanted to show you that rotation. Yeah, let us look at this. See, here we are applying two rotations, right? One is right rotation on 15. When you apply right rotation on 15, what happens? The right of 7 will go to the left of 15, and 15 goes to the right of 7. To the right of 7, you will get 15. To the left of 15, this 14 goes, and to the 6, to the right of 15, it is 16 intact, and this 7 will occupy 15 positions. So above it you will find 6, then there is 5. So again you apply what? A left rotation on the same. When you apply left rotation on this particular tree, what happens now? Here the left, you don't have any left, so if left is there, then that goes to the right of 6, and 6 comes to the left of 7, and 7 will occupy this position. So in that case, what happens? 7 will occupy 6 position, and 6 will come to the left of 7, that is 6 and 5. To the right it is 15, 14 and 16. Okay. Okay. And then above it, to it is nothing but 4 anyway. 4, you have 2, then you have 1, then you have 3. This is what exactly here represented. There are two rotations, right? This is the one rotation, and this is another rotation. After applying these two rotation, you will get the tree like this. Fine. The result was given directly. So first you are applying the right rotation on 15. And then you are applying the left rotation on this particular node, which you get the right root of the same. That's how exactly it is. This is double rotation uh, in this case. I hope this is clear to all of you. So if a sequence of nodes are given to how to insert into AVL and how to delete the same, I hope you can be able to do it. Right? Uh, you know, with another example, it is mentioned here. Just go through this slides anyway. I hope the concept is clear to you. Let us look at the program here. Yeah, if you look at the program, you can see here in the program, as I said, AVL is a binary search tree only, right? It's a binary search tree only, so it'll have both the pointers, left and right pointer. Instead of BST, you are saying AVL. It is now there is a data field and you have a left and right pointer. There is a root pointer, which is static pointer, will always hold the address of the first node, as we know, right? Then then coming to the class, in class we have to find the height, we have a function. To find the difference of height, we have another function, which is nothing but the balance factor, of course. So and then we have four cases, you can see: RR rotation, LL, LR, and RL rotations, right? Of which algorithm I have discussed before. And here the balance factor you're going to identify for each of the node here. You have to insert function, display in order, pre-order, post-order for traversing and printing the same. Now look at the of course in the main function you'll be calling all this function by giving a menu, allowing the user to go for a different choice. You know, if the node is the first one, it will be considered as the root. The subsequent nodes will be inserted into the left or right based on the BST. Once it is done, then you will be checking the balance factor of the same, rather, right? So here the difference of balance factor will be finding by finding the height of both left and right subtrees. You will send the left subtree, right subtree to the height function, and then the you have a height function here, so which will calculate the the height of it based on the left and right height. Whichever is higher, that will be taken into as its height, rather, right? So once you find the height, you will be finding the balance difference of the same in the difference function. Now RR rotation algorithm, which I have just not discussed, right, the same is mentioned here, right? Then LL rotation algorithm is also mentioned here. Fine. LL rotation is nothing but right rotation, right? Right rotation of the tree. Fine. And then you have next is LR. In LR, you will have two rotations, right of you know right subtree, and then uh, you will have, yeah, left of um, left of right subtree and right of root. Similarly, in RL rotation, you will have right of you know left subtree and left of root. Then you can see in the balance is another function where you're going to check the balance factor. If the balance first you're finding the balance factor with the help of difference function here. So once you find the balance factor, you're going to check the balance factor. If the balance factor is greater than 1, it means that it is violating the AVL property. So in that case you will check uh, which particular case it is falling under, rather, right? If it is greater than 1, means it could be greater than 1 means it is 2. If it is 2, then probably it comes under, when it can be 2, basically when it is 2, it could be either LL rotation, that is you can see that the left subtree left pointer is available, okay. And another case wherein the left subtree height is 2, that is here, rather, right, when the left subtree's right pointer is available. So that is what exactly here you are checking the left subtree. If you have the you will be checking here the difference of left subtree height. If it is greater than 0, it means that it is having left subtree. Then in that case, it is single rotation, that is LL rotation. Otherwise, it is double rotation, that is LR rotation. Okay. So similarly, when the balance factor is less than -1, means it could be -2. In that case, again, you will be checking the right subtree, height. So you will be checking here the right subtree height. When it is basically -2, it is in case 2 and case 4 rather, right? Case 2. When it is case 2, you can see this is -2, right? This is 0, -1, -2, right? This is the -2 is happening when the right pointer is available. Okay, when right subtree's right pointer is available, only then it is coming under this case. And when the right is having left rather, right, that is case 4 rather, right? In case 4, this -2 is happening when right left is available. Okay, so that is what exactly you're trying to here ensure. If uh, right subtree height is greater than 0, it means that there is a right of right is available. In that case, it is single rotation, that is and sorry, double rotation. Otherwise it is single rotation, that is RR rotation. Fine. So, and this is the insert algorithm. Insert algorithm is very similar to binary search tree. Create a new node and make both its left and right as null, and you will insert into the node by comparing the root value. If it is less, then moving into its left and or into right. Once you find the parent, you will insert it. Once you do it, you will be calling the balance factor. Once it is done, you will be calling the balance function. So this balance function is what exactly here discussed. It is checking whether that particular node, after being inserted into the tree across the path until it reaches root, is it having the balance factor value exceeding 1? If so, then applying the required appropriate rotations, it will make the tree back into the AVL, and then it will uh, make the tree to be balanced. And post order, pre order, in order, post they are very similar to binary search tree itself, right? Pre order is root left, right, and in order is left root right, and post order is left right root. Okay, and in main function, you are calling all these functions. You can see in the main function, giving a choice for the user with the help of a menu, one with insert, two with delete, display, and three with in order and all kind of thing. So you are allowing the user to enter some item if he is going for a choice one, and insert the same into the AVL. Right, AVL is a class here of which object is created, through which you'll be calling the insert function. So insertion is very similar to BST. After it insert, then it is calling the balance function to ensure that it is balanced or not by taking all the four possible cases into consideration rather, right? That way then you have the subsequent operations to be called at different cases. So I hope this is clear to all of you.